Welcome back to Chips and Salsa, where we talk about all things security at Intel. I'm Crow.
And I'm Jerry.
Hey, Jerry, today we have a pretty amazing little chat with some researchers, 3 of the 10 folks involved in some research called AEX-Notify.
Yeah, so these researchers, the Intel researchers included, presented this paper at the USNIX conference here in August 2023 recently. And a few of them came onto the show to tell us more about AEX-Notify. So let's cut to them and do the intros and find out more about this paper.
Mm-hmm. Welcome to the show, gentlemen. Could you please introduce yourselves to the audience?
Sure. I'm Scott Constable. I'm a research scientist in Intel Labs.
I am Jo van Bulk. I'm a postdoctoral researcher in the TISNET research group at KU Leuven University in Belgium.
Welcome to the show.
I'm Xiang Cheng, currently a fourth-year PhD student in Georgia Tech.
Thank you for joining us, John. So we are here to talk about a paper you all co-authored called AEX-Notify, which was recently presented at the USNIX conference. Can you guys provide our viewers with a high-level summary of the paper?
Certainly. So before anything else, let me just acknowledge something. This paper had 10 co-authors on it. There were 5 from Intel, and there were 5 external researchers, among whom Yo and Sheng were 2 critical contributors. We also had dozens of other contributors within Intel. This was a large effort. It took a lot of people to make this possible. We're grateful to everyone, and it went all the way through, so that's fantastic. Very high level, this paper is about trusted execution environments, which are kind of the building block of confidential computing. So trusted execution environments, or TEEs, use encryption, integrity checking, access control at the instruction set architecture level to protect software that is running within an untrusted or potentially untrusted environment. For example, if you upload your program, your data up into the cloud somewhere, you might be using on the back end trusted execution environments to protect that, for example, from rogue system administrators. And these untrusted environments, they can't read TEE data, they can't read the code, they can't manipulate the data because of integrity checking, but they do control other aspects of the way that programs execute. For example, they have to control scheduling. They have to be able to say, this program can start now, this program has to stop now. And what we've learned over the years since confidential computing was born less than a decade ago is that these untrusted systems can exercise these mechanisms, these controls that they have, in particular scheduling, to execute trusted execution environments at very fine granularity, for example, even at just a single instruction at a time. And part of this paper is decomposing that, getting to the root cause of how that happens. And then the second part of the paper, the solution AEX-Notify, is a mitigation that addresses that set of techniques to exert this fine-grained execution control over trusted execution environments. And in this case, this paper is focused on Intel SGX, which was the first major hardware release of a trusted execution environment.
That's a really great summary. Thanks, Scott. I want to dive in a little bit around the SGX Step tool. It's mentioned several times throughout the paper. Yo, maybe you could talk to us about what is SGX Step and why it's worthwhile to use.
Gladly. So let me pick in on Scott's excellent summary of SGX and enclaves. So I'm going to try to first maybe give you a very high level understanding of what SGX does, and then maybe we can talk a bit more about why it's useful to mitigate this type of tool. So I think the sort of one sentence summary for SGX Step is it allows you to pause an SGX enclave exactly one instruction at a time. And that in itself is not an attack, right? Just execution environments have been designed, as Scott mentioned, to be run on top of an operating system that can pause and resume these enclaves, these just execution environments. But it has been shown that being able to do that very precisely, deterministically even, at single instruction level granularity is a very powerful amplifier. And before we dive into that, maybe let's use an analogy. Let's say that enclaves, we're going to compare enclaves to something in the real world. Let's say a raindrop that's falling, right? So you have a certain event that happens very fast, a raindrop falling with gravity. On Intel processors, we have also very fast events, right? We have Intel processors running at several gigahertz instructions. And what happens when you look at that with, let's say, your plain eyes or even a smartphone camera is that you only see the aftermath of these effects, right? You don't really see the raindrop falling. You see, for instance, the wrinkles in the water after it falls. And it's very similar, I would say, to SGX. If you do certain measurements on SGX enclaves, you will only see things after they have happened because they happen so incredibly fast at gigahertz per second. So what SGX Step gives you is the power of, let's say, a high-speed photography camera. You can really go through it frame by frame and look at all the instances of that raindrop falling, of that instruction going through the enclave. So that's a very powerful tool intuitively, and it has been very widely used as well. So I will spare you perhaps the lower level details of how that works, but it's an open source tool, so interested viewers, listeners can definitely go to SGX Step on GitHub and play with it, as many researchers have been doing.
Cool.
Perhaps it makes sense that I elaborate a bit more on what can be done with the tool as well. So I would say SGX Step allows this pause capability at different levels of granularity. So the highest level of granularity is sort of at a page level granularity. That's an attack that people have shown in academia before. So it essentially means that you can step through an enclave at a 4 kilobyte page level granularity. It's relatively coarse grained and often is used as a stepping stone for doing the more fine grained attacks. These are the sort of instruction level granularity attacks that I think Scott also briefly mentioned. So that's what we call single stepping. So very similar to what you do with a debugger, but this time you don't do it with a debugger because obviously Intel has ensured that you cannot do that on enclaves. But we do it with a neat trick, I think, which is using the timer interrupt to very precisely schedule an interrupt from the privileged operating system into the victim enclave. Single stepping itself then enables a variety of attacks. So top of my head, you can use it to amplify other types of attacks. Think about transit execution attacks like foreshadow or LVI, but also cache attacks and so on. But perhaps more importantly, and also the main focus of being able to count the number of instructions inside an enclave gives you a very surprisingly powerful side channel to deduce things like conditional control flow in the enclave. And finally, mentioning here for completeness, SGX Step also supports what we could arguably call the finest level of granularity, which is zero stepping. And zero stepping intuitively comes down to forcing the enclave to repeatedly try executing an instruction and interrupting it essentially before it had a chance to complete that instruction. And this has been shown by researchers to be very useful to sort of replay certain side effects, things like power consumption. And that means that you can almost infinitively or de facto infinitively replay certain effects that you want to measure, like power consumption. So those are sort of the three main use cases of SGX Step: page level granularity, single stepping granularity, and zero stepping. But in the paper, we focus only on the single and zero stepping, as those are really the fine-grained challenges to resolve here. I think another part of your question was, why does it make sense to protect against it? I think I sort of answered that already, but just to recap, it's a very versatile, widely used tool. In itself, perhaps that's worth mentioning. I would say it's not an attack, it's a tool, it's a methodology to perform attacks, but it has been very powerful. So without that tool, we have seen certain attacks that arguably would be very hard, if not impossible, to exploit in practice. And for instance, on the SGX Step YouTube page, you also will see a demo video that deterministically exploits a very subtle side channel that basically comes down to one instruction difference in a non-constant time memory comparison And I think it's fair to say without SGX Step, that would be very, very hard to exploit, and definitely not at the same sort of the same time frame and determinacy as what we can do with SGX Step.
Sounds like a very powerful tool.
Yeah.
Thank
So, and so the title of your paper, AEX-Notify, it's both the title of the paper and the name of the newest extension to Intel SGX. So, Scott, can you tell us what is AEX-Notify and how that plays out in your paper?
Yes. So first of all, AEX stands for Asynchronous Enclave Exit. The X stands for exit. An AEX is what happens when an enclave exits not of its own accord. So this could either be because of an exception, like a page fault, or because an interrupt has arrived, like from the interrupt controller. And that might have been triggered by the untrusted operating system. So the notify part is that we introduce a small extension to the instruction set architecture of SGX that allows enclaves to receive a guaranteed notification. So after an enclave asynchronously exits, when the enclave is re-entered, it is guaranteed to get a notification that it can use to respond to that exit. And in this paper, we build a mitigation in software on top of that new primitive. So stepping back a little bit to what Yo was saying about single stepping and zero stepping, the root causes of those two are, for single stepping, actually, there's there's an interesting example that comes with SGX Step. It's a slide of no-ops. It's just a sequence of no-op instructions. It's just no-op, 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 no-op. And no-op is like the most trivial x86 instruction. It does nothing. It does nothing except advance the instruction pointer to the next instruction. And intuitively, you'd think, wow, that would execute very fast. If the smallest unit of execution on a processor is 1 cycle, so if you have a 1 gigahertz processor, that's 1 billion cycles per second, a no-op should just take one cycle to execute, right? There are other things that can happen when an instruction needs to execute. And one of those things is something called a microcode assist. For example, if that instruction is on a page that hasn't been accessed recently, we might, the processor might trigger a microcode assist that sets what's called an A bit, an access bit. To indicate that page has now been accessed. And what we found when we were root causing SGX Step is that the microcode assist adds a lot to the latency. It balloons the size of that very small no-op instruction from 1 cycle to hundreds of cycles. So even executing a single no-op on, say, an Ice Lake machine might take 700 or 800 cycles instead of 1 cycle that you'd expect. And that allows a very kind of inaccurate, clumsy mechanism like an interrupt to hit that no-op instruction very precisely. So that's one of the two underlying mechanisms. And then the other one for zero stepping is something like a hardware-driven exception, like a page fault. And the operating system can trigger page faults at will because it controls the page tables. So the goal of this mitigation is to actually address both of those root causes in software. And the way that we do it is we introduce a kind of tickling mechanism where the handler that is invoked when re-entering the enclave, thanks to the AEX-Notify ISA extension, when that handler is invoked, it's going to kind of figure out what the enclave was doing when it was last paused, and it's going to warm up the pages that will be used when we resume back to the instruction where the exit has occurred. So that might include warming up the caches, warming up the TLBs, the page translations for virtual to physical address translation, and preemptively triggering any microcode assists so that those don't happen when we return to the instruction in the enclave application, that those are triggered beforehand in the AEX handler. And by doing that, we take this immense target, this potentially 750 cycle no-op operation, and shrink it back to its much smaller size of 1 cycle. And then it's just too hard to hit with an interrupt. And because we did all the translations and everything beforehand, we're not going to have a hardware delivered exception. So we're not going to have an opportunity for a single step nor an opportunity for a zero step. And that's what this paper is about.
Wow. Yeah, the mitigation uses something brand new we hadn't heard about yet, constant time decoder. Zhang, could you maybe explain what that is, and then maybe describe why it's useful?
Okay, sure. So the constant time the CTD is a constant time decoder, and it is used to help prefetch the pages that are dynamically accessed by the program. So it is constant time means that no matter the input is, its running time and the memory accessing patterns are the same. So if you inspect the program execution, you cannot see the differences when you have two different inputs. We make it constant time because we want it to be branchless and also has its memory access patterns so that we can ensure that it won't leak other further information outside the SGX. Once more, as Stott said, the AEX already takes around 700 cycles in the CPU, so our decoder shouldn't add too much overhead to the whole system as a mitigation. And we finally built it to be around 800 to 1000 cycles to decode one instruction.
Well, that's cool. And I understand that you were one of the original authors of Constant Time Decoder as an intern here at Intel, right?
Yes. It's a great experience doing the intern at Intel. So because of the COVID, although I'm doing the internship remotely, but we have discussions and communications with the team every day to sync up my status to them and also get their feedbacks. And during the internship, although I encountered some challenges in doing this brand new program, but Strout and my manager Mona helped me during the whole internship, and I would say thank you to them for helping me to finish this part.
That's great.
Yeah. So Scott, Intel chose to use both hardware and software together, a kind of a co-design to mitigate SGX Step. Why isn't it enough to just use one or the other?
Yeah, the easy answer for why not just use software is there was no hook to put software. Prior to AEX-Notify, after one of these asynchronous exits occur, the enclave can be resumed at the same point, and there's really no way for it to intercept that event. So that was the software side. On the hardware side, of course, that was the first place that we tried to find solutions. That's where we often apply mitigations wherever there's an issue. That's the first priority. We evaluated several solutions and we discussed them all in the paper. They all had too many shortcomings. Just very briefly, we were able to identify some solutions that could potentially address single stepping, and we could implement those entirely in the processor, either through microcode or something else. But there was really no way to address the zero stepping issue with a hardware only solution. And even with some of those solutions we looked at, there was a very high complexity cost, either we'd have to change the SGX ISA or the foundational ISA a lot, and that would potentially really affect people's ability to make use of it. But actually, one of the other goals that we really wanted to strive for was we wanted to have this mitigation be backwards portable to legacy hardware, to hardware that already exists and is already being deployed and used by cloud service providers, so that we could have kind of an even surface on which our customers can deploy this solution. And the only way that we were able to do it was just to provide this little hook. It didn't take much to implement, relatively speaking, to add this AEX-Notify ISA feature, and then build the more complex part of the mitigation on top of it in software. That was kind of a best of both worlds approach, where we could mitigate both the problems we were mainly concerned about, the single stepping and zero stepping, and have it be at the same time simple enough, feasible enough to backport to some older hardware pieces so that we could have this uniform deployment throughout the ecosystem.
It's amazing. It's one of my favorite parts of doing this show is the chance to talk with researchers such as yourselves, students, and other academics. It's just amazing to kind of see the creativity. I'm curious. Zhang touched on it a little bit, but maybe both of you could share what it was like working with Intel to tackle this problem. Maybe first, Zhang, you could talk a little bit more about what it was like to be an intern, and then Yo kind of talk about it from an external collaborator perspective.
Sure, sure. So as an intern, I finished my internship last year summer and doing it remotely with Intel. So it's a good experience. When I first joined the team, they gave me several topics and projects that I might be interested in. And after comparing each of them, I finally go with Stroud with this AEX-Notify step, and I'm working on this constant time decoder alone by myself with the help of Stroud and Mona. And during the internship, they helped me to get understand of what is, because as you know, this is a brand new terminology also for me, and I'm trying to build the first application that may be applied to many people and many servers in the worldwide. So, and also I faced several challenges during the internship. For example, our first version, which is trying to use the existing constant time compiler to build the program, but its performance cannot meet our requirements. And we discussed together about the new opportunities, and also other engineers, for example, the Cedric, who is also in our paper, helped me to figure out the ways to build the constant time decoder efficiently while also making it constant time. Yeah, that's a good experience to working as an intern.
Cool. And Yo?
Yes, so to complement that, as an external researcher, what I think is the biggest game changer of working with Intel in this project is that you can get access to prototype hardware extensions. And Scott also outlined, right, that this problem cannot be solved in software alone. So I think if you sort of go through the academic literature of the last, let's say, 5 years, you see several attempts of researchers trying to sort of make a step towards a solution there by just using the available hardware. And none of these, I would say, are principled, mostly because they try to reuse legacy hardware that was never intended for this purpose, things like the transaction synchronization extensions that you find in some Intel processors. So what really was a game changer here is to get access to the prototype hardware and work together on the software part. I think I also really appreciated how Intel was very committed to understanding the root cause of the issue. Again, contrasting that to let's say, existing academic work that was mostly focused on mitigating the consequences, things like detecting with heuristics suspicious interrupt rates. What this solution really does is to prevent the exploit in the first place, which I think is the right way forward. What I can also say here, I think, is that it's inspiring to work with a large team where I think internally Intel has all the expertise on the ISA and whatnot. Very often we had discussions on very small, let's say, weird types of features in x86, and as an independent researcher, you're often a bit in the dark there finding that out, and Intel has all the expertise to work on that, of course. I think also what distinguishes this project obviously from, let's say, the average research project is that this was really intended to go into production. And I really enjoyed working on, let's say, not just the main thing, but also all of the edge cases. And we have found, I think, a number of very interesting edge cases that we could flesh out together. So that's a very, I think, enriching experience to work on an actual product as well.
That's very, very cool.
Yeah. Like Grob said, one of our favorite things to do here on the show is talk to academic researchers, and it's really always cool to kind of hear your experiences working with Intel and collaborating with Intel engineers, and that's cool. So, question for all of you: AEX-Notify is a generic hardware feature, and you wrote a specific software mitigation that uses AEX-Notify to address a specific set of issues. Have you seen any other uses for AEX-Notify?
I'll say one thing really quickly first is that simply by virtue of the ISA that was added, even just enabling AEX-Notify can provide a small performance boost to enclaves, especially enclaves that have to handle a lot of exceptions. because the ISA extension changes the control flow, the path for handling exceptions, and makes it much more efficient while providing semantically the same behavior. So even just by enabling it, exception handling gets faster. I think we reported in the paper, at least on our platform, between like 70 and 85% faster.
Huh.
So does your paper cover any other uses though for AEX-Notify?
I was going to leave that to Yo and Chang. Do you have any ideas?
Well,
You're the researchers, the younger minds.
I think there are plenty of ideas, right? I think, and I hope to see that in the next, let's say, years, the research community will jump on this and come up with things that we cannot even imagine at the moment. I really hope to see that. What I think is sort of the elephant in the room, we also briefly described it in the paper, is this problem of page fault side channel attacks. The ones that I mentioned earlier briefly, the 4 kilobyte granular ones. We explicitly in this project set that out of scope because we have to, for the academic paper, make a convincing case that we actually solve that. And in the current software mitigation, that is not included. But I think the software mitigation includes very valuable elements, building blocks to make another software mitigation that builds on AEX-Notify that would include that. So I think that is something that I hope to see arising as a next step. There are a number of other things. We also described them briefly in the paper. Things like cache attacks could be mitigated. I think it would be interesting to think about more general microarchitectural states cleansing and restoration, perhaps on context switches. And apart from that, I'm also just very curious to see how this propagates in the software ecosystem. So at the moment, the mitigation is upstreamed in the Intel SDK. That is still, I think, the biggest sort of standard SDK out there, but there are a number of other solutions out there, some building on the SDK, some from scratch, and I think it will be interesting to see how different software projects are going to incorporate that. And related to that, what I think would also be interesting is to improve our let's say, confidence in the software solution by applying things perhaps like formal verification and so on. So I think we will see all of these lines being explored in the next years, hopefully.
That's great.
I think
Chang,
maybe Xiang wants to say something on the constant time decoder.
Yes, for the constant time, actually, I think there are two opportunities for the future research. The first one is that although we made this constant time decoder to be fast, but due to time and energy limitations, there are still some uncovered instructions. And I would happy to see if we can finally make it perfect or there are other opportunities to improve it. And another part is about the optimization. Do you remember our first version that we are using an existing constant time compiler to build the program? However, its performance cannot meet our requirements. So I think there are opportunities to make those optimizations added to the existing compiler so that next time we won't spend our time and energy on writing it in the complex way, but simply build it.
Excellent. So again, to the group, what are some next steps to see this get implemented?
Well, it's already mostly implemented. The hardware already exists. So this is we have Sapphire Rapids that was launched earlier this year. That's getting AEX-Notify in a patch. We have Emerald Rapids coming later this year, and that's going to have AEX-Notify built right into it. We are also doing some backports, as I mentioned, to older hardware. So there are some older coffee-like platforms that are typically used for servers, things like CSP, cloud service provider usages that already have it, and we expect that more will get it in the future. On the software side, as Yo mentioned, the mitigation has already been upstreamed into the Linux SGX SDK. It's a baseline version of the implementation. We're still working the constant time decoder through the review process, and there's a pull request on GitHub right now that's almost all the way there. I expect it'll be there, if not by the end of this month, by the beginning of September, and then that'll be it. We'll have it all up there.
Nice.
So as we kind of wrap up here, can can you just give us a summary statement of, for the end customer, what is it that they're being protected against, and, how does this benefit them?
So 2 things. Number 1 is the goal of this mitigation from the beginning was to address these fine-grained execution control techniques that execute 1 enclave instruction at a time or 0 enclave instructions at a time, and use that to amplify or enhance various kinds of side channels, including timing side channels, power side channels. And by taking away that primitive, we take away a critical point of leverage for those attacks. And then number 2, as I mentioned briefly, is you can get a small performance boost, especially if your workload, whatever you're running, if it has to handle a lot of exceptions. And there are some types of enclave workloads, like things like enclavized containers, where that is something that frequently happens. So you can get a small performance boost.
Awesome.
Well, I want to reiterate what Jerry said, that this is really some awesome work. We really appreciate all of you and the extended team that also helped with this paper. We appreciate your time kind of explaining your research and then explaining what some of the benefits are to users of these systems. So thank you all.
Thank you, too.
Thank you.
Thank you, Yo. Thank you, Shang.
Thank you.
Wow. I just love these sessions where we get to talk to these folks. It's just amazing how brilliant and just how curious these folks are and the solutions they come up with.
Yeah, and I love the ongoing collaboration between Intel and academia. It's just it's a great way for academics to get access to engineers and hardware that they might not have otherwise, and it just helps them learn more so that their research can be more productive, and the collaboration is always great.
And like Yo said, it was really impactful to him to actually see the solution developed and help see, he had an idea, a problem they found, and it was actually see it get fixed.
Yeah, and to get implemented into actual products. So it's got to be pretty cool.
Yeah.
But that's it for this episode of Chips and Salsa. Thanks for watching, and we'll see you next time.
All right. Bye.